All right, example 10 is going to use the half-life formula. You can see here that as well as these other formulas, you got all these variables. We need to know what the variables represent. Initial amount, final amount, the requirement of the units there is they're the same. So it's grams, grams, ounces, ounces, whatever. Half-life is h and t is the elapsed time, and it has to match the half-life unit. So if the half-life is given in days, t would be in days. If it's in years, t is in years, and so on. So these units match, but the half-life of an object is what it is. So, you know, if it's carbon-14, 5,730 years. If it's polonium-214, I believe is what it was we saw yesterday, 1/10,000th of a second. Okay, that's how you what you'd use. But that's the half-life formula. 0.5 1/2 to t over h power is what happens times the initial amount, and that's the way you'd evaluate too. So that times that to that power, then multiply, gets you the final amount. So with that in mind, find the age of a bone if it now has 85% of the carbon-14 it had when t equals 0. So what we want to have is the amount final is 85% of the amount initial. All right. One way of doing that is to start off with 100 for the initial amount, ending up with 85 for the final amount. That's 85% of 100 is 85, right? Another way of doing that is to start off with 1 to begin with and 0.85. Take your pick. They're both 85% of this. I prefer to go with 1 personally. So 1 times 0.5 to the t over h. And again, carbon-14 is the way we date things, and 5,730 years is the half-life of carbon-14. So 0.5, we don't know what t equals, but 5,730 is carbon-14's half-life. Okay. For carbon dating specifically, you just do the same formula. This same formula just puts a 5730 there. On the test, it's carbon dating is the problem involving that, so the 5730 is given. So the half-life formula for carbon dating, they actually put the 5730 there on the bank there, so you don't have to remember that number. All right, so at this point, because this is a 1, that 1 really isn't not necessary to be written. That gets us to that structure we're looking for. We have the exponential expression equal to the number. So all we have to do is log both sides, and this is not base e or base 10, so you can take your pick of which log. I like ln. So ln of 0.85 on the left equals ln of 0.5 to the t over 5,730 on the right. And as always, if I have log of an exponential expression, the power can be pulled out in front. So I end up with ln of 0.85 equals t over 5,730 ln of 0.5. And our task is to find out what t equals. I got to divide by ln of 0.5 to get that over there, and I got to multiply by 5,730. I can do it several steps or one step. But if you just imagine this is like a fractional coefficient here, multiplication by 5,730 over ln of 0.5. Same thing here, 5,730 over ln of 0.5. That accomplishes getting rid of 5,730 and ln of 0.5 over here. And my result is just that whole thing. So 5,730 ln of 0.85 divided by ln of 0.5. That's the point where I would probably come over here to my calculator and start entering stuff in. It's been asked, should we put that up as the power? If you do 0.85 to the 5,730th power, it'll equal 0. Okay, so it's better to leave that out. Just evaluate this times this divided by that. So 5,730 times ln 0.85 in parentheses divided by ln 0.5 in parentheses. We get 1,343.485903. And you get the answer your calculator says. Then you do want to round. If it specifies, it says, it doesn't say, right? So it's that many years. Typically they say round to the nearest 10, round to the nearest whole number, that kind of thing. Let's just go nearest 10. So 1,340 years.